We want to understand the purpose of the scientific method. We want to know the difference between qualitative and quantitative observations. We want to be able to describe the difference between hypotheses, theories, and models. And so what is a scientific method? It's a logical approach to solving problems by observing and collecting data, formulating hypotheses, testing hypotheses, and formulating theories that are supported by the data. This is a step-by-step process, guys, that all scientists use. And it is important to recognize that it is a step-by-step process. It's important to recognize that it actually has to be done in the correct order for it to be the scientific method and to do what it is that we desire the scientific method to do and provide for us. So what are these steps? We start with observations. We start by making observations. We cannot do the scientific method. We cannot formulate hypotheses out of thin air. Okay, so observations are basically using the senses to get information. And the information that we collect is called data. And data can fall under two categories. It can be qualitative, it can be quantitative. Qualitative data is descriptive. We can talk about the color of what we're looking at. We can talk about whether it's a solid or a liquid or a gas, but it's definitely descriptive. Quantitative is numerical. Quantitative data is specifically connected to ultimately the measurements that we are making, the measurements that we are taking, and that gives us numerical data that is called quantitative. Okay, everything that we're studying, the definition here is a specific portion of matter in a given region of space that has been selected for study during an experiment or observation. What we are looking at, what we are studying, what we are observing, what we are collecting data on, this is called a system, and we talk about these things in science in terms of the system that we're looking at. We move from our observation making to actually formulating a hypothesis. And our book here is going to define a hypothesis in terms of making generalizations about the data and then moving from generalizations to formulate a hypothesis or a testable statement. And the book is going to tell us that a hypothesis very often is an if-then statement. I want to actually go a little bit deeper on this, guys. A properly understood hypothesis is a logical explanation of the observations we've made. We make observations, and then can we explain what those observations are? And a logical explanation of what we observed is a better understanding of what a hypothesis is. Then we need to be able to make a prediction, and very often the prediction, which is not the same thing as the hypothesis, because the hypothesis is an explanation. The prediction based in the hypothesis is usually an if-then statement. And this is what we use, our hypothesis and our prediction. They need to be very logical. They need to be worded very tightly, because then we move on to an understanding of how we can test our hypothesis based on the prediction. So I want you to understand those subtle differences, guys. And how we test the hypothesis is actually conceptually us now moving into the experimental phase. And what we do is we actually design experiments that will allow us to collect the data based on the prediction that we made, recognizing that the prediction is based on the hypothesis. And this will then ultimately help us to be able to support or refute the hypothesis or the theory that we're talking about. And a good experiment needs to have controls and variables. And the controls are conditions in the experiment that always remain the same, always remain constant, whereas the variables are experimental conditions that change. And in fact, the variables should be the specific things that you're testing in terms of your your prediction and your hypothesis. And in fact, you should try to design an experiment such that you have it limited so that you're only testing one variable at a time, so that you can actually look for and identify cause and effect relationships. And moving on to theorizing, once you've collected data as you've run your experiment, we create what we call models. Models in science are not just physical objects, but models are explanations, or they're diagrams, they're ways of understanding phenomenon or the relationship between data and events. Models can be visual, they can be verbal, they can be diagrammatic, they can be mathematical. Okay, an atomic model of matter, what I referred to in the first chapter as the particle theory of matter, it's just that, it's an explanation and understanding of matter based on the fact that it's made out of atoms. Okay, from our working out these models, okay, then we move into a theory, which is a broad generalization that explains the model or the body of facts or the phenomenon. It explains everything that we've been able to find and then write up. And an example of a theory would be the atomic theory. That is the theory of how atoms are actually made. Okay, what makes up atoms? And again, we find that based on our model, which is based on the data we collected, explaining from our experiments the different hypothesis we had and the predictions that came from that hypothesis. And all of this follows quite clearly here. All this follows from this flowchart where you see we have observations being made, and those observations are going to lead to the formulating of a hypothesis, which will classify. They'll be predicting, and that leads to testing. And if the testing creates data that doesn't support the hypothesis, notice you move back to your hypothesis and you rework it. If the testing does, and you move on to theorizing, where you're constructing models and you're communicating, even making more predictions, ultimately publishing your results, which is communication, which then, if you see back, leads back to more testing, and that testing being more scientists from around the world who now have this information, working on trying to confirm what you've done and what you have found. All right, now we're going to look at the units of measurement. And here, what I want you guys to be able to do is distinguish between a quantity, a unit, and a measurement standard. We're going to be able to name and use the international standard units for length, mass, time, volume, and density. We're going to distinguish between mass and weight, something that we've already done a bit. And we're going to look at density calculations. And we're going to transform a statement of equality into a conversion factor. And this is all, now we're kind of getting into the heart and soul of the types of problems you're going to do in chemistry. You're going to need to be able to do these and apply all of these properly and appropriately. Units of measure. It's important to remember, guys, here, measurements represent quantities, but they are not quantities. A quantity is something that has a magnitude, size, or amount. So you've got to understand, it's a subtle difference, but it is there. When we measure something, we're representing the quantity, but we're not actually giving the quantity. Okay, so measurements and quantities are not the same thing. Teaspoon is a unit of measurement. Okay, volume is a particular number, which is a quantity. And how you choose and use your units is going to depend on the quantities that you are measuring. So SI stands for International Standard. Basically, the French is there if you know how to pronounce it. I'm not going to try to pronounce it here. I wouldn't want that to be recorded because I'm sure it's going to sound awful. But it's the standard that all scientists use around the world. So those of us in this class who are Americans, we're going to have to start moving away from the English system of measurement and start thinking a little bit more broadly, seeing how what we're studying is science. Okay, and there are 7 base units. And then all the other units are mostly going to be derived from those 7. So let's take a look at those. Here they are. Length, symbol is lowercase l. abbreviation is M for meter. Mass symbol is lowercase m, abbreviation is kg for kilogram. Time symbol is lowercase t, abbreviation is s for second. Temperature symbol is uppercase T, abbreviation is K for Kelvin. Amount of substance, the abbreviation or the symbol is N, the abbreviation is MOL for mole. Electric current, ampere, you see that as A, and luminous intensity, candela, CD. We won't deal with electric current and luminosity much in this class. Now with mass, it's the measure of the quantity of matter, and the SI standard for mass is the kilogram. Okay, weight is the measure of gravitational pull on matter. So mass does not depend on gravity. Mass is how much stuff is present. Weight is how much gravity is pulling on it. So if I weigh 230 pounds on Earth, I weigh considerably less than that on the moon, and I weigh considerably more than that on Jupiter. Okay, but if I have 5 grams of some substance, if I have 5 grams of soil, it is 5 grams on the Earth, it is 5 grams on the moon, it is 5 grams on Jupiter. It doesn't change. Doesn't have anything to do with gravity. It's just the amount of stuff that is present. So it's important that you know that difference. Basically, in chemistry and in science classes, you're going to deal with the mass and not the weight so much. Although in physics, you would deal with the weight a little bit more, I would think, but possibly not. Everything is really going to be talking about mass. Length. Length is a measure of distance. The SI standard for length is the meter. The kilometer is used to express longer distances. A centimeter is used to express shorter distances. Again, you need to know these. Now we can derive units. We can talk about area, volume, density, molar mass, molar volume. Probably won't deal with energy much. But these are derived because they're a combination of one sort or another of two other ones. So area is length times width. So the unit is meter squared or square meter. Okay, volume is length times width times height. So now you're talking about cubic meter. Density is mass over volume. So it's kilogram over cubic meter, or kilograms per cubic meter. Molar mass is mass over amount of substance. So it's kilograms per mole. Molar volume is volume over amount of substance. So it's cubic meters per mole. This is what we mean by derived. These are combinations of SI units. Okay, and then there's pressure, which is measured in kilograms per meter times second squared. That doesn't make sense. I think that's a typo. I'm going to look that up. But pascals is usually what we'll use if we do pressure. And we will talk about pressure in a lot more detail when we get to the gas chapters. All right, volume. Volume is the amount of space occupied by an object. And we said the derived SI unit is cubic meters. We can use the cubic centimeter. But the liter is a non-SI unit. So even though the liter is the metric unit for volume, okay, it's not the scientific standard for volume. So you're going to have to understand conversion, right? If you have 1 liter, it's the same thing as 1,000 cubic centimeters. If you have 1 milliliter, it's the same thing as 1 cubic centimeter. And that's important because we're going to talk about conversion and conversion factors. Density, the ratio of mass to volume, or mass divided by volume, looks like that. There's your formula for density, D equals M over V, mass over volume. And therefore, it's going to be kilograms per cubic meter. That's going to be the derived unit. We can also use grams per cubic centimeter and grams per milliliter. And density is a characteristic physical property of a substance. What we mean by that is the density of a substance will always be the same under the same context or circumstances. We can actually identify unknown substances by figuring out their density. This chart actually gives us known, these are all densities at 20 degrees Celsius or room temperature. Notice copper, it's 8.92. It's always 8.92. If you have some substance and you want to figure out what it is, one of the things we'll do in a chemistry class is we will always determine densities. And then we can look up and we can see, well, I find the substance, it's got a density of 8.92. Very well could be copper. That's what we mean by characteristic physical property. So let's look at our first sample problem. A sample of aluminum metal has a mass of 8.4 grams. The volume of the sample is 3.1 centimeters cubed or cubic centimeters. Calculate the density. So what this looks like, you should write out what you're given is. You're given a mass and you're given a volume. Your unknown, what you're trying to find in this case, is density. Write out your formula, plug it in and play, and do the math. Make sure you keep track of your units. And you get 2.7 grams per cubic centimeter, which is your density. That brings us to a discussion about conversion factors. Okay, these are important. A conversion factor is a ratio derived from the equality between two different units that can be used to convert from one unit to another. An example, how do we understand what that means? Well, quarters and dollars. Okay, we know that they're two different units, but there is an equality. A certain number of quarters equals $1, okay, and vice versa. And we can write those equalities out. 4 quarters equals $1. So 4 quarters over $1 equals 1. $1 over 4 quarters equals 1. We also can write it out. $0.25 over 1 quarter equals 1. And 1 quarter over $0.25 equals 1. By understanding that equality, we can then create these factors that will allow us to convert. And you're going to take this concept, guys, and you're going to apply it to your problems in chemistry, because you cannot work problems with different units. You cannot multiply kilograms and grams. Okay, you've got to be able to convert. You always have to be working apples to apples, oranges to oranges. Always. This leads us from conversion factors to dimensional analysis, which is a mathematical technique that allows you to use units to solve problems involving measurements. How do we do this? We start with the quantity sought, and the quantity sought will always equal the quantity given times the conversion factor. That's dimensional analysis by definition. If we stick with our examples of quarters, we can do an example, the number of quarters in $12. Well, you have to do a dimensional analysis problem. The number of quarters equals $12 times the conversion factor. What's your conversion factor? What do you want to do? You want your answer in quarters. And this is the rule that you should always apply. You want your answer in quarters, so you need to set it up to get rid of the dollars. So your conversion factor is going to be 4 quarters over the dollar, because you've got dollars on the top, dollars on the bottom. They cancel out. 12 times 4 quarters is 48 quarters. You can set up every chemistry problem the same way, and you will be expected to. This chart shows you in more scientific terms, how do we use conversion factors? Well, identify the quantity and unit given and the unit that you want to convert to. Okay? So, number 1, your quantity and unit given, you've got 4.5 kilograms. You want your mass in grams. You figure out the equality that relates to the two units, which is kilograms to grams. You set up your conversion factor so that you cancel out the given unit and leave the unit you want. So in this case, it's 1,000 grams over 1 kilogram, so that you have kilograms on the top and kilograms on the bottom. They cancel out. Then you multiply and you carry your unit over to the answer. And so 4.5 times 1,000 is 4,500. You carried your unit over. It's grams. We can also derive conversion factors if we need to know the relationship between the unit you have and the unit you want. So what are the conversion factors for meters and decimeters? You just need to know the relationship. 1 meter equals 10 decimeters, which is the same as saying 0.1 meter equals 1 decimeter, which is the same as saying 10 decimeters equals 1 meter. And what you put on top and what you put on bottom is strictly a function of which unit you want to cancel and get rid of and which unit you want left in your answer. This chart is in your book, and it shows the relationships, remembering the basic unit, meter, seconds, ampere, mole, candela. Okay, and these are just prefixes that will show you, you can see where the different relationships are from giga to mega to kilo to centi to milli to micro to nano to pico. Everything's going to be based on 10, so everything is related, and your conversion factors will be based on that as well. So here's another sample problem. Express a mass of 5.712 grams in milligrams and in kilograms. So here you have, that's what you're given. You want to get the mass in milligrams and kilograms. Let's solve it for milligrams first. We know that 1 gram equals 1,000 milligrams, which means you can have one or the other on top. You need to decide which one you're going to have on top based on which unit you want to cancel out and which unit you want to have at the end of the problem in your answer. In this case, you want grams on the bottom because you want to get rid of grams. You set it up, 5.712 grams times 1,000 milligrams over grams. Your 2 grams cancel, meaning your answer is going to be in milligrams. You do the math, 5,712 milligrams. We set it up again, start out the same way. This time you want to solve for kilograms. You know that 1,000 grams equals 1 kilogram. You know that you're either going to have it set up one way or the other, depending on what you want to get rid of. You're going to pick again with the grams on the bottom, because that's what you want to get rid of. You set up the problem, 5.712 kilograms times 1 kilogram over 1,000 grams. Notice again your grams cancel out, your kilograms carries over into the answer. You do your math, which ultimately this time is going to be 5.712 divided by 1,000, and you get your answer.